Welcome. This is the third video in the series of estimation theory, and in this video I will talk about efficiency and sufficiency. These are the two characteristics for an estimator to be a good estimator. In the previous two videos I have talked about unbiasedness and consistency. So let's start. In case if you are new to the channel, do subscribe it because here you get good quality video content. So let's first talk about efficient estimators. Even if we confine ourselves to unbiased estimate, there will be in general more than one consistent estimator for a parameter. For example, in the sampling from a normal mu sigma square population where sigma square is known, sample mean is an unbiased and consistent estimator of mu. This is a multiple choice question information that for a normal population, sample mean is an unbiased and consistent estimator of mu. It is also known, or it can be shown, that sample median is also an unbiased and consistent estimator of mu. Right. Now both sample mean and sample median are unbiased and consistent estimator. So it means what? That there is a necessity of some further criteria which will enable us to choose between the estimators with a common property of consistency. Such a criteria which is based on variance of the sampling distribution, right, of estimators is usually known as efficiency. Let me talk about very important points here, and this slide is very important for multiple choice. The first point is that what happens, that suppose you are looking for an estimator and you have identified a number of them, and all of them are satisfying the characteristic of being unbiased and consistent. Now you have the option, so which one should you select? Then in that case certainly you will look for one characteristic which is other than the common characteristic, right? Now that characteristic I will consider as efficiency. So that efficiency is based on what? It is based on the variance of the sampling distribution. So this question is asked that efficiency is based on which characteristic of sampling distribution. So it is based on efficiency of the sampling distribution. And here the two statements that I have highlighted in red, that sample mean is an unbiased and consistent estimator of mu, and sample median is also an unbiased and consistent estimator of mu. I will show that there will be one characteristic which will help us to choose between sample mean and the median, which is the efficiency. So if the two consistent estimators T1 and T2 of a certain parameter theta if variance of T1 is less than variance of T2 for all value of n, then we say that T1 is more efficient than T2, right? So what is the definition of one estimator being more efficient? That if we have two estimators like T1 and T2, and both of them we are using to estimate theta, and if we have shown that variance of T1 is less than variance of T2, so the one which is with less variance is more efficient. Yes or no? So that is the definition of efficient estimator. Now the previous example that I was talking about, that if I talk about sample mean, it was both unbiased and consistent. So for a large value of n, what is the variance of x bar? Variance of x bar is sigma square by n. We have shown it in previous two videos that if x follows the normal distribution with parameter mu and sigma square, then x bar follows the normal distribution with parameter mu and sigma square by n. So the variance of x bar is sigma square by n, and variance of the median is given by pi sigma square by 2n. This can also be proved. So which is nothing but 1 by 1.57, because pi by 2 is 1.57 by sigma square by n. So you can see that if I'm taking about variance of x bar, which is like sigma square by n, it is less than the variance of the median, which is 1.57 into sigma square by n. So the variance of x bar is less than variance of median. So from this we can conclude that the sample mean is more efficient estimator for mu than the sample median. So this can be asked as a MCQ question, that which one is the more efficient estimator. So you have to remember that the sample mean is more efficient estimator. Why? Because the variance of sample mean is sigma square by n, and variance of sample median is 1.57 into sigma square by n. So the variance of sample mean is less than the variance of sample median. Okay. Now, what do you mean by the most efficient estimator? So if in a class of consistent estimator for a parameter, there exists one whose sampling variance is less than any such estimator, it is called the most efficient estimator. So whenever such an estimator exists, it provides us a criteria for measurement of efficiency of the other estimators. So what is basically the information that they are trying to pass on to you? That suppose we have a number of estimators like T1, T2, Tn, and each of them are consistent and unbiased, and I want to check that which one is the most efficient. Then the one with the least variance will be the most efficient, right? In life also, if I can take this example, that whom we will consider a better friend, the one who shows the least variance, because their behavior remains throughout. If someone who is a Maverick, like one day he is very happy, another day he is very sad, one day he is very helpful, another day he is very angry, so that kind of friend you don't want in your life. You want the one who is showing the least kind of variance, and if someone who is showing their pattern or behavior in a very similar line, they will be considered as most efficient, right? Now what is the definition of efficiency? So if T1 is the most efficient estimator with variance V1 and T2 is any other estimator with variance V2, then the efficiency of T2 is defined as variance of the first estimator, that is V1 and V2. Since we know that V1 is the most efficient, so the variance of certainly V1 will be less than V2. So if V1 is less than V2, then obviously E cannot exceed unity. So the efficiency of an estimator cannot be greater than 1, right? Because efficiency will always be less than 1, right? Because in the numerator we are taking the most efficient estimator variance, and the estimator which has least variance is the most efficient. So certainly for any other estimator the variance will be greater than V1, so V1 by V2 will be less than 1. So these are important thing for multiple choice question. Now with this basics, we are going to solve two quick problems related to efficiency, and these are very important problem, has been asked multiple times in different exams. So we have a random sample of size 5 drawn from a normal population with mean unknown mean mu. Consider the following estimators to estimate mu. So we have three estimators, T1, T2 and T3. In T3 we have the parameter where we have a constant lambda, where lambda is such that T3 is unbiased estimator of mu. So the first question is we have to find lambda, right? Second question is are T1 and T2 unbiased, and third question is state giving regions the estimator which is the best among T1, T2 and T3. So let us solve this. The information that is given to us, that expectation of xi is equal to mu, and variance of, here they are using this capital X, so let me write, so expectation of xi is equal to mu and variance of xi is equal to sigma square, because we are drawing it from the normal population, right? Now the first question is that T3 is unbiased estimator of mu, so find lambda. So it is given that T3 is unbiased. So what is the property of unbiased estimator? That expectation of T3 should be equal to mu, right? So this implies what? That expectation of T3, which is equal to 2x1 plus x2 plus lambda x3 divided by 3 should be equal to mu. So this implies what? Using the properties of expectation, I can write it 2 by 3 constant, the coefficient of x1. So it is 2 by 3 into expectation of x1. Coefficient of x2 is 1 by 3, so it is 1 by 3 into expectation of x2, and plus lambda by 3 into expectation of x3 is equal to mu. They can ask this in MCQ exam also. So now expectation of xi for all I, this is true for all I, is mu, so it will be like what? It will be 2 by 3 into mu. The second term, expectation of x2 will be also mu, so 1 by 3 into mu, and lambda by 3, expectation of x3 will also be mu. So this whole thing is equal to mu. So you see the 2 by 3 mu and plus 1 by 3 mu. So that is equal to mu. So I will take lambda by 3 mu, and if I take this 2 in the right hand side, I will get mu minus mu is equal to 0. So from this, mu is not equal to 0, so I will get lambda is equal to 0. So the first answer is that find lambda. So we have got lambda is equal to 0. Okay. The next part of the problem is, are T1 and T2 unbiased? So to check that, I am using a different color. So now to check whether what is the expectation of T1. So if expectation of T1 will be mu, I will say that T1 is unbiased. So let us calculate expectation of T1 is x1 plus x2 plus x3 plus x4 plus x5 divided by, this whole thing is divided by 5. Yes, so I will get what? I will get 1 by 5, and using the properties of expectation, I can write expectation of x1 dot 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 up to expectation of x5, and I have already agreed that expectation of xi is equal to mu, so this will be equal to 1 by 5, and mu expectation of x1 is mu, expectation of x2 is also mu, x3 is also mu, x4 is also mu, x5 is also mu. So I get 1 by 5 into 5 mu, so that is equal to mu. So expectation of T1 is equal to mu, so T1 is an unbiased estimator of mu. Now the next part is that what about the next estimator T2. So I have to calculate expectation of T2, and that is equal to expectation of T2 given to be x1 plus x2 by 2 plus x3. So this will give me what? This will give me 1 by 2 into expectation of x1 plus 1 by 2 into expectation of x2 and plus expectation of x3. So this gives me what? Expectation of x1 is mu, so 1 by 2 into mu. Expectation of x2 is also mu, so 1 by 2 into mu. Expectation of x3 is mu, so that is equal to mu. So what we get is 2 mu. So expectation of T2 is equal to 2 mu, which is not equal to mu. So it means what? That this implies T2 is a biased estimator, not unbiased. It is a biased estimator. Okay, T2 is a biased estimator, because for it to be a unbiased estimator, it should be equal to mu. Expectation of T2 should be equal to mu. So we have answered two part, what is the lambda, and are T1 and T2 unbiased. Now we have to decide that which is best among T1, T2 and T3. So I have checked their property, that is unbiasedness. Now the next thing you might be thinking that what about consistency? So as you know that in the previous video you have studied this, that consistency is a characteristic which is associated with infinitely large number of infinitely large value of sample size. So for the larger sample size, so here the consistency will not come into picture because we are taking a small samples, right? So the next thing that we have to talk about is the efficiency. So how do you decide efficiency? Efficiency is based on the variance of the sample. So I am calculating the efficiency of variance of the different estimators. So the first estimator is 1 by 5 into x1 plus x2 plus x3 plus x4 plus x5. And if you remember the property of variance, 1 by 5 is the coefficient of x1, x2, x3, x4 and x5 all. So I will take 1 by 5 square outside. This is the property of variance. And here I will get variance of x1 dot dot up to variance of x5. Right, I hope you will write the details. So it is 1 by 25, and what is the variance of x1? That is sigma square. What is the variance of x2? Sigma square. We already have taken this here in the beginning, that variance of xi is sigma square, because we are taking the sample from a normal population with mean mu and variance sigma square. So what did I get? I got 1 by 25 into 5 sigma square. So I am getting something like sigma square by 5. So that is the variance of T1. How will I calculate the variance of T2? So variance of T2 will be variance of x1 plus x2 by 2 plus x3. So what is the coefficient of x1? 1 by 2. So it will be 1 by 4 into variance of x1. What is the coefficient of x2? That is 1 by 2. So it will be 1 by 4 times variance of x2. And what is the coefficient of x3? That is 1. So it is 1 times variance of x3. So now variance of x1 is sigma square. So I will get 1 by 4 into sigma square. 1 by 4 into sigma square and sigma square. So it will become 3 by 2 times sigma square. And let us calculate the variance of T3. What is T3 here? T3, I have got lambda is equal to 0. So it is 2x1 plus x2 by 3. So variance of 2x1 plus x2 by 3, because for it to be unbiased I already have taken lambda is equal to 0. So the coefficient of x1 is 2 by 3, so it will be like 4 by 9 into variance of x1, and coefficient of x2 is 1 by 3, so it will be like 1 by 9 into variance of I am writing v only for variance. So variance of x2, so 4 by 9 sigma square and plus 1 by 9 sigma square. So what I get? I get 5 by 9 sigma square. So variance of T1 is sigma square by 5. Variance of T2 is 3 by 2 sigma square, and variance of C3 is 5 by 9 sigma square. So which one is the least? Sigma square by 5 is the smallest value. This is 1 by 5, this is 5 by 9, and this is 3 by 2. So we note that since variance of T1 is least, so T1 is most efficient, and hence the best estimator. So you can write it here, best estimator, right? So this is how we have to use the property of variance to decide that which estimator is the best estimator. I have calculated, I moved to the previous slide. So yeah, so we have calculated using the property of variance that since this one is the least, so it will be the best. If you are least, you are the best. Okay. Now let us quickly solve this problem also. And it is a similar problem, that x1, x2, x3 is a random sample of size 3 from a population with mean mu, variance sigma square. T1, T2, T3 are the estimators used to estimate the value mu, where T1 is this, T2 is this, T3 is this, are T1 and T2 unbiased estimators. So let us write the first one. What is expectation of T1? So expectation of T1 is expectation of x1 plus x2 minus x3. So that is expectation of x1 minus expectation of plus expectation of x2 minus expectation of x3. So that will give me what? We are taking from the normal population, so mu plus mu minus mu, so that is equal to mu. So first, is T1 unbiased? So this implies T1 is unbiased, because expectation of T1 is equal to mu. Now what about T2? So I will calculate expectation of T2. So that is expectation of 2x1 plus 3x3 minus 4x2. So that is 2 times expectation of x1 plus 3 times expectation of x3 minus 4 times expectation of x2. So I will get 2 mu plus 3 mu minus 4 mu. So that is equal to mu. So it means T2 is unbiased. So both T1 and T2 are unbiased. The answer is yes. Are they unbiased? So the answer is yes. Next part, find the value of lambda such that T3 is unbiased estimator of mu. So expectation of T3, if it to be, for this to be unbiased, should be equal to mu. So this implies expectation of 1 by 3 into lambda x1 plus x2 plus x3 is equal to mu. So this will give me what? This will give me 1 by 3 lambda expectation of x1 plus 1 by 3 into expectation of x2 plus 1 by 3 into expectation of x3 is equal to mu. So this will give me what? This will give me 1 by 3 into lambda mu plus 1 by 3 into mu plus 1 by 3 into mu is equal to mu. So from this I will get, this is 1 by 3, 1 by 3, 2 by 3 mu. So I will get 1 by 3 lambda mu is equal to mu minus 2 by 3. So that I will get 1 by 3 mu. So you can cancel. So what I will get? I will get lambda is equal to 1. So for lambda is equal to 1, T3 will become unbiased. Okay. Now with this value of lambda, is T3 is a consistent estimator. So if I take this value of lambda means what? Then the T3 will become what? T3 will become 1 by 3, and if I take lambda is equal to 1, it will become x1 plus x2 plus x3. So it will become x1 plus x2 plus x3. So this is basically what? This is the mean of the sample. This is the mean of the sample. Okay. So we know that sample mean is a consistent estimator of population mean. We have seen it in the previous video. So since T3 gives us the sample mean, I can write this line: since sample mean is a consistent estimator of population mean, so T3 providing us the sample mean, T3 is a consistent estimator. Because the property is basically associated with large sample, means if you increase the sample size for larger sample, then sample mean is always a consistent estimator, right? Now the fourth property, the fourth part of the question is that which one is the best estimator. So again we are going to calculate the variance. So variance of T1 will be what? Variance of, and T1 is x1 plus x2 minus x3. So I write x1 plus x2 minus x3, and this is equal to variance of x1 plus variance of x2 and plus variance of x3. A student will make mistake. I hope you remember which property of variance I am using. I am using the property of variance of ax plus b is equal to a square into variance of x. So whatever is the coefficient of x, that becomes a square. So here the coefficient of x3 is minus 1, so it will become minus 1 square, that is 1. So it will be sigma square, this will be sigma square, and this will be sigma square, so it will be 3 sigma square. If I ask you what is the variance of T2, so T2 will be like what? T2 will be 2x1 plus 3x3 minus 4x2. So variance of 2x1 plus 3x3 minus 4x2. I hope I have written it correct. x1, x3, x2. So 2, 3 and minus 4. x1, x3 and yeah. So this will be like what? This will be 4 times variance of x1, 2 square, plus 9 times variance of x3, and minus plus, so plus 16 times variance of x2. So this will give me what? This will give me 4 sigma square plus 9 sigma square plus 16 sigma square. So that will give me 29 sigma square. And if I talk about variance of T3, variance of T3 will be variance of 1 by 3 into x1 plus x2 plus x3. So this will be like 1 by 9, variance of x1 is sigma square plus 1 by 9 sigma square plus 1 by 9 sigma square. So the total will be 1 by 3 sigma square. So as you can see that even though the T1, T2 and 3 all are unbiased, variance of T3 is the least. It is 3 sigma square, it is 29 sigma square. So since variance of T3 is least, so T3 is the best estimator, or what term they are using? They are using which is the best estimator. So since variance of T3 is least, so it is most efficient and most efficient, so it is best. So I think you have understood the efficiency topic very well, and here I discussed about certain thing. This is a very important topic. So efficient estimator, most efficient estimator, and the problems. Now the next thing that we are going to talk about is sufficiency. So sufficiency is the last characteristic for estimator to be good estimator. I already have discussed about unbiasedness, consistency and efficiency. Okay. So let us talk about the sufficiency characteristic quickly. So an estimator is said to be sufficient for a parameter if it contains all the information in the sample regarding the parameter. See what happens that when we are doing any analysis, carrying lot of data is also a difficult task, right? So we want to make an estimate based on that data set or that sample, so that we do not lose any information about the population. Just to give you a kind of analogous explanation, suppose you want to know about your blood report, okay, and so you want to go for a blood test. So if you go for a blood test, what do? You take a small sample, or you give a small sample, just they take 1 drop or 2 drop, and based on that they give you the report of your blood. It is not like that they take all blood out of your body and then they give you the report. Yes or no? Means the blood report can be generated with the help of a just 2 drop of bloods also. So in case of sufficiency also, we are looking for that characteristic which is going to contain all the information about the parameter, right? So this is a way to understand. Let us look at the mathematical way, that if T, which I am defining with the help of a sample x1, x2, xn, is an estimator of the parameter theta based on a sample of size n from a population whose density is given by f of x theta, such that the conditional distribution of x1, x2, xn given T is independent of theta, then T is sufficient estimator of theta. Means the conditional distribution of x1, x2, xn given T should be independent of theta. Okay. Now there is a important result that is known as factorization theorem, and it helps us to find the sufficient estimator. So the necessary and sufficient condition for a distribution to admit sufficient statistics is provided by the factorization theorem due to Neyman. So what is the statement of the theorem? That let T is equal to Tx is sufficient for theta if and only if the joint density function L of the sample values can be expressed in the form L is equal to g theta Tx into Hx, where as indicated g theta Tx depends on theta and x only through the value of Tx, right, and Hx is independent of theta, right. So g theta Tx depends on theta and x, and with the help that Tx is defined with the help of x, so that is what it is saying, that it depends on theta and x only through the value of Tx, and Hx is independent of theta. One thing I want to highlight here, that it should be clearly understood that by a function independent of theta, we not only mean that it does not involve theta, but also that its domain does not contain theta. So for example, if you look at this function, you can say that this function does not contain theta, but this function is defined in the interval a minus theta to a plus theta, means the domain involves theta, so I will consider that this function depends on theta. Okay. Sorry. Now the invariance property of sufficient estimator. We have seen the invariance property of consistent estimator in the previous video. Here it is a slightly different one. So if t is a sufficient estimator of parameter theta and psi t is a one-to-one function. In case of consistent, it was a continuous function, but here it is saying that if psi t is a one-to-one function of t, then psi t is a sufficient estimator for psi theta. So you remember this result. It may be asked that which of the following is the invariance property of a sufficient estimator. This will be clear to you. I mean, when I'll be solving the problem, the mathematical aspect will become clear to you, so don't worry. There is something called as Fisher-Neyman criteria. So a statistics T1, which is based on a sample x1, x2, xn, is a sufficient estimator of parameter theta if and only if the likelihood function or the joint density function can be expressed as g1 of t1 theta into k of x1, x2, xn, means where g1 t1 theta is a PD of the statistics T1, and this is a function of the sample observation only, independent of theta. So you need to remember this result, but to understand it better, we are going to take some problems, and that problem will help you to understand the concept better. So watch till the very end. In case if you are feeling like this is a very complicated thing, don't worry, you will be able to understand it. So the first question is that let x1, x2, xn be a random sample from a population whose probability density function is given by this. We have to show that this is sufficient for theta. So how to do that? There are steps here. So we are going to use the factorization theorem. So what is the factorization theorem? That is suggesting us that we are going to write the density function, a joint density function. So how do you write the joint density function? And this is important because we are going to use this in case of maximum likelihood estimate also, that I will be discussing in the next video. So I will be writing the joint density function of x theta. So let me write like this: L of here the function is defined as f of x theta. So let me write L of x theta. This is equal to the product of I varies from 1 to n, and here we take the probability density function. So f of xi theta, right? So it is equal to what? It is equal to product of I varies from 1 to n, and f of xi theta is equal to theta into xi to the power theta minus 1, right? Now if I take the product of these things, what will I get? I will get this is equal to theta will come n times, so it will become theta to the power n, and here x1 to the power theta minus 1, x2 to the power theta minus 1. So basically let me write it, otherwise you will get confused. x1 to the power theta minus 1 into x2 to the power theta minus 1 dot 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 xn to the power theta minus 1. So what we can do, we can write is theta to the power n, and then this whole thing x1 into x2 into xn can be taken to the power theta minus 1. So this thing I can write as theta to the power n product of I varies from 1 to n xi to the power theta minus 1. What is my aim? My aim is to write this in the form of two function g theta. Let me show you that statement here. We want to write it in terms of g theta tx and hx, right? So I want hx to be free from theta, and this value is depending upon theta and tx in turn is depending upon the sample value. So basically what I am trying to do, if you look at this expression, it is not like free from theta, right? So I am rewriting this, and this is the main point which you need to understand. So what you can do, you can write it theta to the power n, and into uh, pi product of xi, I varies from 1 to n whole to the power theta, and it is minus 1, so I will write 1 by pi xi, I varies from 1 to n. First of all, I hope you agree if I write it like this, because I have divided it by this. Now you will think that what is the purpose of writing behind this. So now you look at this expression. So this expression here is dependent on theta and tx. So here we are writing it, I am writing it with a different thing. I am calling it g theta tx. And what is tx here? Here I am writing in this side because we don't have the space, where tx is equal to pi into I varies from 1 to the power n, I varies from 1 to n xi, where tx. So it is g theta tx, this is a function of theta in terms of tx, right? And into this thing can be written as a function, the second thing can be taken as hx, where hx is equal to 1 by pi I varies from 1 to n xi, right? Because this thing is just dependent on the value of x, that is x1 x2 xn, that is the sample value. And here this thing I am calling g theta tx, because it is theta to the power n, and this term I am calling tx, so it is tx to the power theta, so which I am writing as g theta, because it is a function of theta which is depending upon tx, right? So if I am able to write this joint density function like this, we will say that the t1, or here this term I can call t1 also, because in place of here in the statement they are using t1, so let me call this tx as t1. So what we get t1 is equal to product of xi, I varies from 1 to n, is a sufficient estimator or sufficient for theta, right? So this thing is important, that here actually tx is being defined with the help of the sample value, and this much of information is sufficient to get the value of lx theta, because you see if I know what is this product, I can get L of x theta, the joint density function, because theta is known, so theta to the power n, and this information that we require, so I can write it t1 to the power theta into 1 by t1. So this will become the sufficient estimator for theta. Now let us look at this problem quickly, and I think with the help of this you will be able to understand it completely. So here again, if I have to write the solution, what I will do, first I will write the joint density function L, that is the product of I varies from 1 to n and 1 by theta, and f of xi theta, so it will be e to the power minus xi by theta, right? So I hope you will be able to write it directly, 1 by theta to the power n, and it will be e to the power so x1 into theta into e to the power x minus x2 by theta. So I can write minus 1 by theta and summation of xi. Okay, now this thing I can write as what? So here if you look at this term, it is depending upon both theta and x. We don't have any term which is independent of theta. So what we can do, I can write it, let me first write and then I will explain. I am writing it g theta tx, okay, and into hx, where I am taking h of x is equal to 1. I can write it this thing into 1, and I'm considering h of x is equal to 1, so it is independent of theta. And if you look at this expression, in this expression, what is the value of tx? So the value of tx is basically summation of xi, right? So we can write, so here this tx is equal to summation of xi, because this function that I have taken, this function, it is depending on the value of tx, and it is a function of theta and tx. So what is the tx here? Tx here is summation of xi. So what is the sufficient estimator? So here we can conclude that summation of xi is a sufficient estimate of estimator for theta. Some of you might be thinking that I could have taken minus of summation of xi. I am considering that it is minus of 1 theta, so this part is I am including with theta. Okay, let us quickly take this result, and all these examples are very important, so listen it very carefully. Now if you look at this result, let x1, x2, xn be a random sample from a normal mu sigma square population, and we have to find two values, two estimators. One is for mu and another is for sigma square. So here the theta actually is two things. Here theta, there are two parameters, one is mu and another is sigma square, and we know that mu lies between minus infinity to infinity and sigma square also lies between minus infinity to infinity. So here when we talk about the parameter theta, we are basically looking at two parameters, two values, that is mu and sigma square. So like always we are going to write L. How do you write L? You write the joint density function. So the product of I varies from 1 to n and f of xi theta. Do you remember the normal distribution joint probability density function? If you do not remember, no problem, I am writing here. It is given by 1 by sigma under root 2 pi and e to the power minus 1 by 2 sigma square into xi minus mu. This is xi minus mu whole square, because I am writing f of xi theta. So if you simplify it, it is 1 by sigma under root 2 pi, and this is going to come n times, so it will become 1 by sigma under root 2 pi whole to the power n, and here it is e to the power. In the numerator you will get 1 minus 1 by 2 sigma square common, and you will get summation of xi minus mu whole square. I varies from 1 to n. I hope you have understood this term. Now this thing can be written as what? This thing can be written as 1 by sigma under root 2 pi whole to the power n and e to the power minus 1 by 2 sigma square, and here if I expand this, I will get what? I will get I varies from 1 to n xi square a square minus 2ab. So minus and here I am writing one step directly, so I will write minus 2 mu into summation of xi. I varies from 1 to n, because if you take 2x1 mu, 2x2 mu, so 2 mu will be cancelled, sorry, 2 mu will be out of summation, and I varies from 1 to n, and plus mu square will come n times, so it will be n mu square. This thing I hope you have understood. Now what I can do here, if you look at this expression, this is neither free from x or nor free from mu or sigma square. So what I can do, I can write it as g theta, where theta is mu and sigma square, so it contains both mu and sigma terms, so I will write g theta tx, right, and into what is hx? So hx is we don't have any term which is just independent of no mu and sigma, so here I am considering the hx is equal to 1, right. So if you look at the next expression, I have to move to the next page because we don't have a space here. So let us look at that. So this whole thing that I have got here, this I am calling g theta tx, and hx is equal to 1, because here it is not independent of theta terms. By theta I mean both mu and sigma square. So what I am going to do in the right in the next page, I have written it. So you see I have written g theta x is 1 by sigma under root 2 pi and e to the power minus 1 by 2 sigma square, and here what I am doing, I am taking this this term, that is which is kind of defined with the help of the sample values, that is summation of xi. I varies from 1 to n, and then we are taking this term which is also defined with the help of sample values, that is xi square, right? So I have written this next term as t2. So for this term, that is sigma x square summation of xi, I am calling this term as t2x, because here the tx actually contains two term of kind of sample values. One, it is a set which contains t1x and which also contains t2x, right? So basically there are two functions of x which I am defining with the help of sample values. One is summation of xi square and another is summation of xi. So this is what I have written: t2x minus 2 mu t1x plus n mu x mu square, and hx is equal to 1, right? So we have this tx. Let me write it one more time. So we have the tx, which is nothing but t1x and t2x, because we want to estimate two parameters, and which is nothing but summation of xi, which I am calling t1, and summation of xi square, which I am calling t2, right? So what we conclude? So we conclude that t1 which is equal to t1x, which is equal to summation of xi, is sufficient estimator, is sufficient for mu, and t2x, which is summation of xi square, is sufficient for sigma square. I hope you have understood this, because if you look at this term, if we want to calculate, if suppose mu is given, how did I kind of concluded that this is for mu and this is for sigma square? So if suppose mu is given, right, then if we know xi square, I will be able to estimate kind of sigma square. But if suppose sigma square is given, right, so sigma square is given means summation of xi square, we need to know that only, then only we can calculate sigma square. So it means we can just conclude that summation of xi is a sufficient estimator for mu, and summation of xi square is a sufficient estimator for sigma square. So this was an important problem. I hope you have understood this. So just in all the three problems, what I am doing, we are writing L, and we are writing L as the product of the joint density function f of xi theta. Means this is the product of the density function, and this is also known as joint density function. And after that, we are trying to write the product in the form of g theta tx into h of x, right, into h of x, where h of x is dependent on just x values, and g theta x is dependent on theta, and tx, where tx is dependent on the value of x, right? So let us quickly look for this problem, and after that I will conclude this video. So here let x1, x2, xn be a random sample from a Cauchy population, which is given by 1 by pi into this. Examine if there exists a sufficient statistics for theta. So like always, we are going to define n, and n will be defined as I varies from 1 to n into 1 by pi dot 1 by 1 plus xi minus theta whole square. Here we have x, so we are writing xi minus. So this will be equal to what? This will be equal to 1 by pi to the power 1 by pi whole to the power n, right? So because pi is going to come n times, so it will be 1 by pi to the power n. And this will be product of what? This will be just product of I varies from 1 to n 1 by 1 plus xi minus theta square. Now as you can clearly see that in this case it is not possible to write this as a product of g theta tx, right, into hx, because how will I write it? It is dependent on xi and theta both, right? And we can't get any hx which is free from xi, sorry, which is free from theta. So we can't get any hx kind of term here. And here also you will not be able to if you expand it, you will not be able to separate this term xi and theta, because if you expand it, you will get what? You will get 1 by 1 plus xi square minus 2xi into theta and plus theta square. So you see, you are getting xi square and you are getting 2xi theta. So you are not able to filter out or get the term tx which is depending on just x. So this L cannot be written in the form of this expression. So the factorization theorem will not work here, and so we can conclude that hence by factorization theorem, there is no single statistics. There is no single statistics. Statistics means something which is associated with the sample. Statistics which is sufficient estimator for theta, which is sufficient for theta, right? Because if you again I repeat that if you expand it, you will get 1 by 1 plus xi square minus 2 xi into theta plus theta square. So you will not be able to filter out something which is which can be considered as tx, right? And so if it is not possible, you will not be able to write it as g theta tx into hx, right? So I hope the things that I have discussed in this video is clear to you. Yeah, sufficiency is a slightly more engaging kind of concept. So this is the third video, and in the first I discussed unbiasedness, in the second I discussed consistency, in the third I discussed efficiency and sufficiency. So in the next video I'll be talking about the maximum likelihood estimator, which will be one of the most important topic. So that's all for this video. Thanks for watching and have a great day.